Today we're going to talk about two terms that are used interchangeably in ordinary life. People use the words accuracy and precision as if they really mean the same thing. In other words, good. Something that's accurate is good. Something that's precise is good if it's an instrument or a machine or something like that. But accuracy and precision to a scientist are different things. They're both good, but they're different. They mean different things. Accuracy means how close the average of your measurements are to a true or accepted value. So that's the key. If you know what the number is supposed to be, you know what the measurement's supposed to be, your device is accurate if it actually gives you something close to that number. That's what accuracy means. We can think about accuracy and precision in terms of a target. If you think about a rifle has the ability to be accurate and the rifle has the ability to be precise, or possibly both. Now let's use the idea of a rifle to explain the difference between accuracy and precision. Is this an accurate rifle? Well, let's think about the meaning of accurate. Accuracy is how close the average of your measurements are to a true or accepted value. For shooting a rifle, the true or accepted value, of course, is the bullseye, right here. That's where the shots are supposed to hit. Well, if you average these two shots, they're right on the bullseye. If you average these two shots, right on the bullseye. And then we have another one that's right in the center of the bullseye. So is it accurate? Well, yes, it is. It agrees very well with the target. Is this an accurate rifle? Again, think about the meaning of accuracy. The average of the values should be close to the true or accepted value. Well, this shot and this shot average about there. This shot and this shot on average are about in the middle. And then there's another one that's right in the middle of the bullseye. So both of these rifles are accurate. A lot of people wouldn't think that this second one is accurate, but it is. On average, it's hitting the target right in the bullseye. Well, what's precision? Precision, on the other hand, is how well your measurements agree with each other. So for something to be precise, it doesn't have to necessarily even have a true or accepted value, let alone match it. The values just have to agree with each other. They have to be close to each other. Again, we can think about a rifle. Is this a precise rifle? Well, do the shots agree with each other? They do. They're in a very tight grouping, and that grouping happens to be on the bullseye, but that's not what makes it precise. What makes it precise is that the shots are close together. Let's look at another rifle. Is this a precise rifle? Well, if I look at this group of shots here, it is very close to each other. It's not on the bullseye, but that just means it's not accurate. Precise just means that the shots agree with each other, or the measurements agree with each other. So precise means close together, accurate means on target. Let's apply this to some scientific measurements. Let's say the true and accepted value here is 10. Which of these sets shows a greater accuracy? Well, we'd have to know what the averages are, and I think we can do this without actually averaging them. If you look at these numbers, roughly, I would say the average is going to be somewhere between 1.5 and 2.5. If you look at these, well, probably if you average them all, it's going to be pretty close to 2. But this average and this average, neither one of them is very close to 10. However, if I average these numbers, I would probably come up with something that's about 10. Two of the numbers actually are 10. Here's one that's 2 below 10, here's 2 above 10, and here's one that's 1 below, and here's 1 above. So that would average to 10. So, which is accurate? It's this group that's accurate. Here's the same 3 sets of measurements, but now the question is different. The true value is still 10, but which set shows greater precision? Well, this ranges from 8 up to 12. 8 to 12 is a spread of 4 entire points. This ranges from 1.98 up to 2.01. That's only 3/100ths. This ranges from the low of 1.3 to a high of 2.9. So this is closer than the last group, but the middle group has the smallest spread. In other words, in the middle group, that's where the numbers are most closely in agreement with each other. So that group is the most precise. It's not accurate if the true value is 10, but it's more precise. Now, which is better, accuracy or precision? If you know anything about buying rifles, you are more interested in a precise rifle than an accurate rifle, because accuracy, you can fix that. If a rifle is not precise, there's not much you can do about that. Same thing is true for scientific instruments. Precision is very important because in many cases, if you're doing real science, you don't even have a true or accepted value, so you only can rely on your precision. So how do we tell each other about our precision? Well, chemists use this method called significant figures. When they report numbers, they use this fairly efficient way of reporting precision that's built right into the way they write the numbers. Here's how it works. When you're reading an instrument, you report all the digits you know for sure, plus one more digit that's an estimate. Here's an example. If I'm reading this thermometer as precisely as I can, here's what I know for sure. I know that the tens place is as high as 60, but is not as high as 70. So I know that for sure. Tens place is 60. Now, I don't know for sure what goes in the ones place, but I can estimate. If I kind of guess how far this is between the 6 and the 7, I would guess that it's probably 8/10 of the way. So the ones place, I'm going to call that 8. So in other words, I would report 68. So the tens place I know for sure, 60. The ones place I estimate as 8. I report 68, and that gives me two figures that are significant, two significant figures. The digits that I reported that way are called the significant figures for that measurement. Now here's a different thermometer, but it maybe has the same temperature. This thermometer gives me more precision. Here again, I know the tens place is for sure 60 and not 70. I also know for sure that the ones place is 1, 2, 3, 4, 5, 6, 7. So I know for sure it's 67. I know the tens place is 60, the ones place is 7. The tens place is where my estimation comes in. And I'm going to guess that I'm 8/10 of the way between 67 and 68. So I write down 67.8. The tenths place, 8, is an estimate. I report the whole number, 67.8, the two digits I know for sure, plus the one that's an estimate, and that gives me 3 significant figures. Here's another thermometer. It's even more precise. Now, again, I know for sure that my tens place is 60. I know that my ones place is 7 because I have a marking here that's labeled at 67 and it's not quite to 68. So 67 I know for sure. But now I have a line every 1/10 of a degree on this thermometer. So I'm 1, 2, 3, 4, 5, 6/10. So the tenths place I also know for sure, and that's 6. So I estimate. Looking between 67.6 and 67.7, I'm guessing I'm 9/10 of the way. So I will estimate that. I report all 4 of my significant figures for a total of 4 sig figs. Writing the numbers down this way is a way of reporting precision. So let's say that my thermometer reading came right up to here, and I thought it was right at 68.3. I would not write 68.3 because I want to report that I have the ability to estimate to the nearest hundredth. I would write 68.30. In writing the number that way, I'm reporting precision to the hundredths place. So when you write numbers, and when you read other people's numbers, more importantly, you have to have some rules to follow that this whole system works by. Here's one of them. All zeros that are to the left of the first non-zero digit are not significant. So, for example, if I had this number, 0.00010, all the digits that come to the left of that non-zero 1 are not significant digits. They have to be there because 10 and 10/100,000 are completely different numbers. They're placeholders, but they're not significant figures. So zeros to the left of the first non-zero digit are not significant. Here's another rule. We only have 3 rules. All zeros to the right of a non-zero digit, but just to the left of an implied decimal point, are not significant. So if I have this number here, 1200, written this way, if I actually were to write the decimal point, this is where it would be. but it's not really written. It's what's called an implied decimal point because it isn't really there. When that happens, what we're reporting is that we don't have precision out to where that decimal point would be. So those digits, because they are to the right of the non-zero 2, but immediately to the left of that implied decimal point, they're not significant. So this only has two significant figures, the 1 and the 2. On the other hand, if I wrote the number this way, with a decimal point at the end that's not implied but actually expressed, then that's telling me that I know the number all the way out to the nearest 1. That's my limit of my precision. And so this actually has 4 significant figures. The third rule is very simple. Every other digit is significant. So the only digits that can ever be non-significant are zeros, but that doesn't mean that all zeros are not significant. Let's look at a few examples. How many significant figures do you think are in 202 pounds? Well, this 0 would be insignificant if it came to the left of the first non-zero digit, but it doesn't. It could also be insignificant if it came immediately to the left of an implied decimal point, but it doesn't. And so it's significant. And in fact, all 3 digits are significant in this number. How about this one? If you guess that the first 3 digits are not significant, you're right. Zeros that come to the left of the first non-zero digit are not significant. And so this only has 1 significant figure, just the 2. Try this. Well, the zeros that come to the left of the first non-zero digit, these first 2 zeros are not significant. But these zeros are not to the left of an implied decimal point, nor do they come to the left of the first non-zero digit. So that means they are significant. So now we have 3 sig figs in this number. Another way of thinking about this is there's no good reason to write those 2 zeros there because they don't change the number at all, except unless you want to report how precise your measurement is. Try this. The last 2 zeros are not significant because they come to the right of a non-zero digit, the 2, but immediately to the left of an implied decimal point. Decimal point's not really there. So this only has 1 significant figure. Here's 200 again. Are the sig figs the same? Well, here the decimal point is actually written. That means something. That means that we know this number out to the nearest 1. And so we have 3 significant figures here. They're all significant in this measurement. Of course, you aren't only going to read and write numbers. Mathematics is the language of science, and math often involves calculations. So we need some rules for how to handle these numbers and calculations so that our precision doesn't get too big, bigger than it really is in real life, or too small, sloppier than it is in real life. So we have 3 rules for calculations as well. The first rule applies to adding and subtracting. When you're adding and subtracting, you want to round your answer to the decimal place of the least precise measurement in the problem. So here's an example. Let's say I was adding 219.4539, which is good out to the nearest 10,000th. And I'm going to add to that the number 12, which is good only to the nearest 1. If I just add this up without thinking about significant figures, here's what I get. 9, 3, 5, 4. 9 and 2 is 11. Carry the 1. This becomes a 3, and this stays at 2. Now, if I write my answer, 231.4539, what I'm really telling the reader is I know that the real value is somewhere between 231.4538 and 231.4540. But that's really not true, because this number here, I didn't know that any closer than just to the nearest 1. So I can't really narrow it down that tightly. The rule says I have to round this off to the decimal place of the least precise measurement in the problem, which is the 1's place. So here's what I write. 231 reports the proper precision. The second rule applies to multiplying or dividing. When you're doing that, round the answer to the significant figures of the least precise measurement in the problem. So this is different. Instead of going by decimal places, when you multiply and divide, you go by the significant figures. But it's still, you go by the least precise measurement, and that's so that your precision doesn't get more and more precise as time goes on. So here's an example. Let's say we're doing this multiplication problem. 13.0 times 1.2. Let's pull down a calculator and do this. So I put in 13.0 times 1.2, and my calculator doesn't know the rule, so it gives me all the digits that it needs or that it has room for, which is 15.6. 15.6 has 3 significant figures in it. If you look there, there are 3 significant figures. Well, my answer should be rounded to 2 significant figures, because 13.0's got 3, 1.2 has got 2, so my answer's got to be rounded to 2 significant figures. 15.6, I would round to 16, because 6 is more than half, so that's how I'd report that. Let's look at a division problem. Let's say I were doing 120.0 and dividing by 12. 120.0 has got 4 significant figures in it. 12 has got only 2 significant figures in it. So when I do my division problem, this should be 2 significant figures. Well, if I divide 120 by 12, I'm going to get 10. So I'll write down 10. But 10 written this way has only 1 significant figure in it. So I've got to put a decimal point there to show 2 significant figures of precision. The third rule is a very easy rule. Counting numbers, or exact numbers, have infinitely many significant figures. So let's say I'm doing this problem. 3.653 pounds per chicken, and I'm multiplying by 10 chickens. Well, 10 chickens is a counting number, and it's considered exact. So therefore, when I multiply these together, I'm going to get pounds, but I'm going to go by the significant figures in this number, because this has infinitely many significant figures. It's not rounded off, it's not a measurement, it's a count. So my answer would be 36.53 pounds of chicken. I would keep all 4 significant figures that I have in that first measurement. Try this one. Well, here's how you calculate this. 3.65 times 12 would give you 43.8. Now, if you think about how many significant figures you should have here, this number, 3.65, has got 3 sig figs in it. They're all significant. 12 inches per foot, that's an exact number. There aren't 12 inches in a foot because somebody measured a foot and found out that it was 12 inches long. There are 12 inches in a foot because we define a foot as 12 inches. So that's an exact number. So this has infinitely many significant figures. We don't count it in sig figs, we go by the 3. So my calculator tells me 43.8, which is 3 sig figs, and I'll use all of them. What's the unit? Feet drop out of here, and it's going to be inches. Here's another one. Well, this is an addition problem. If I add together 20,000 and 5.25, using my rules for significant figures, I have to round off to the least precise of the 2 measurements. Well, this is good to the nearest cent. This is only good to the nearest $10,000. So when I add these together, I don't really have to do the arithmetic. 5.25 is so small compared to 20,000 that my answer is, to the correct number of sig figs, $20,000. And I don't put a decimal point at the end because that would give me too many significant figures. I'm rounding off to the nearest 10,000. This is actually an important thing to know because a lot of times scientists can get out of doing arithmetic entirely by just knowing what answers aren't going to make a difference. It's really important in adding and subtracting.